in actin or thin filament right here. You do have these a little bit bigger protein molecule, look like tennis balls. I'm making an analogy, or balloons, whatever you want to make. These are the protein molecules called actin molecules, and these actin molecules are connected together by a rope. Protein molecules look like a rope. Have you seen those balloons? They flame up and they tie them up together. They twist them. Have you seen that in, I don't know, parades or other events? That's it. You're looking at one right here. So these actin molecules are connected together by that protein molecule tropomyosin. It's called tropomyosin. And every so on and so forth throughout the actin molecule, you see these little protein molecules called troponin complex. They're like a ping pong. If these are tennis balls, these are like ping pong balls. If they're like a balloon, this would be like tennis balls. I don't know. I'm making analogies. Ping pong balls, small protein molecule called troponin complex. 3 of them scattered out throughout the actin. That's it. I'm done. And then, of course, these guys, the actin molecules are attached to what? Z line. The actin molecules are attached to what? Z line. From Z line to Z line is called what? Touchdown. Very good. You guys are with me. So come here. Very good. You're with me. Thank God. I should go home tonight and pray God 10 times more, because you're all with me. If you are not with me, then, oh boy, I should go home and cry. Put my head on the shoulder of my wife and cry and say, I was talking today, I was spilling my heart. I worked very hard, but they were not paying attention. Their mind was not here. The body was here, yeah. They took the quiz, but their mind was not here. I said, my wife tapped my shoulder and said, don't worry, honey. Next exam, they do better. For example, I'm saying for example. These things never happen, but I'm just making it up as we go along. I cannot make up anything I talk about here, right? So I'll make up other stuff. Okay, so here they are individually. The myosin is made up of these protein molecules. Here they are, and they are the next thing, the next few slides, I guess, I want to talk about, and then we end up the lecture right here after I talk about these things. Come on. This one, this is something you should know, and we'll talk about it. I will give you all of the details here in a minute. This is when a muscle is relaxed, and this was your second muscle question today, the discussion question today. First one I asked, what is histology of muscle? Second question I asked you today, how is muscle being contracted? Muscle contraction. Right now, my biceps is relaxed, not completely, but right now is what? Contracted. I'm going to talk about this. Right? Yo, am I with me? Am I with me? I'm tired of saying, are you with me? So I'm going to say, am I with me? Are you with me? Well, okay. So right here, the muscles, the myosin is not attached. The big difference. Let's look at the big picture. And then we go smaller, and hopefully during exam you write me the small one, not the big ones. Here are the head of the myosin attached to the actin on this one. No, here they are. Okay? And I'll tell you in a minute what happens that they do attach there. Okay? Another thing. Are the actins closer to each other on the contracted muscle or on the relaxed muscle? On contracted muscle, they're closer to each other. I'm contracting my muscle. So from Z line to Z line is shorter or longer on the contracted muscle? Shorter. Z line to Z line is shorter. Am I making some sense so far? You're going to go forward question by question. Now, what is the A band? A band is what? Look at your notes. Make me proud. The what? Where you have both what? Actin and myosin. And what is the IBAC? Huh? Where you have only actin. Am I making some sense a little bit? Now, tell me this. When the muscle is contracted, what do you think happens to the fate of the A band? Is A band changes its dimension, becomes bigger or smaller? I should write these things on the board. I know you probably cannot see it. What happens to A band? I should draw it on the board. I'm going to write it and then you'll see it in a minute. A band does not change. I know this doesn't show it very well. Does not change. I band, on the other hand, shrinks, becomes shorter. And then what happens to Z line? Z line is what? Where there is only what? Did I give you that? I guess I didn't give you that. Z line, if you go back, as not Z line, sorry about that. He did not give it to you. It's called H zone. H zone, where there is, I should write it down. H zone, H, this is H zone, where there is only myosin. And you know about A and I. So shorter, I band gets shorter during muscle contraction. And Z line, what happens to Z, I say Z line, Z lines get closer together. H zone, shorter, and some textbook, it depends, some textbooks say it disappear. Does it make sense? A little bit. If it does not make any sense, if you look at this, the Z line to Z line is shorter during contracted muscle. The A band does not matter. It's the same size, stays the same, does not change, stays the same. It changes, but I should say stays the length of it. This is all length. A band length stays same. I band becomes shorter during muscle contraction, and then Z shorter. Z band becomes shorter. Okay. If not, during lab, if we still is puzzled, I will draw this on the board for you. Okay. Here we go. So what happens? A few things. So that happened during muscle contraction. This is, go back to the material from last week's lecture. So these are vesicles. This is an axon knob. Axon knob, muscle. Axon knob, inside of it you have neurotransmitter. Neurotransmitter is what? Acetylcholine. They diffuse. Acetylcholine is released. They go to the muscle. I will not mention T-tubules, then that would be too much information. It goes to the muscle, and inside of the, and then these acetylcholine cause sodium to get into muscle cells. When sodium rushes into muscle cells, then what will happen on this diagram, Schwann cells, of course, release the neurotransmitters. You have sarcoplasmic reticulum, have calcium inside of it. Calcium is released from sarcoplasmic reticulum because there is abundant sodium inside of muscle cell. Now you have action potential in muscle cell. I hope I'm making some sense. Now you have action potential in muscle cell. And then when calcium is released from sarcoplasmic reticulum, then those calcium will go attach to troponin complex. When they attach to troponin complex, the shape of the actin changes. When the shape of actin molecule changes, they rotate, then the head of the myosin attached to them. When the head of the myosin attached to them, they release, but before they release, they pull up. They attach right here. The head of myosin attached to the actin, and before before they release, they pull them. And release, pull them. Release, pull them, so muscle becomes shorter. That's what they call it, attack, pull, release. And these are a sequence of events shown to you. And anytime you want to detach, the head of the myosin from actin, you need ATP. For attachment, you need calcium. All is needed, calcium from sarcoplasmic reticulum attached to troponin complex. You don't need ATP. Okay. Then here is a sequence of events, very short, summarized, nice and beautiful. Here is axon knob, release acetylcholine. Acetylcholine causes sodium to come inside of muscle cell. And then when sodium comes inside of muscle cell, inside of sarcoplasmic reticulum, you have calcium. A lot of calcium are released. They attach to the actin. The shape of the actin changes. As you can see, the Z line come together. The H zone disappear. The head of the myosin attaches to the actin and pulls the actin toward each other. At the end, when it's all over, again, you need ATP, back in biology 1 again. You need ATP back into sarcoplasmic reticulum, and you need ATP for that. When calcium is going back from sarcoplasm into sarcoplasmic reticulum, you need ATP. For calcium to go back. I hope I'm making some sense. I know it's the end of the hour, you're getting tired, I can see it in your face. It's amazing when I'm up here, what I can see in your faces. I've been doing this for how many years? 20, 30, 40. Since 1984, I lose track of it. My advisor from Tennessee takes me, Amir, how old are you? I just had a birthday last month. Amir, how old are you? I said, Dr. Patton, I don't know how old I am. They come and go so fast. But I tell you, I was born in this year. I will not tell you. I was born in this year. You do the calculations. So I've been doing this for a long time, and I can see it. You're tired. That's okay. And now at Delta College, amazingly, they want to extend the lecture hours. 1 hour. They say, oh, 1 hour is not enough. We're going to extend it to 1.5, 1 hour and 20 minutes. Oh, God, please don't. Whatever you do not. Next year, they're going to. I'm not going to say it, but anyway. So make sure, I already talked about this. I will come back and revisit this next time at the beginning of the hour. Please remind me, Amir, you can go over muscle contraction one more time, and I will. And your quiz stops right here, homeostasis. But make sure you know it. I will go over it again quickly, 1 minute. Next lecture on Thursday, but 1 minute. I'm not going to spend 20 minutes on it. Okay, and then this is where we stop. And that's where your quiz on Thursday is going to stop. Do I make sense?